Let's go over the whole of AQA nuclear physics. We're going to start off with Rutherford scattering. So Rutherford used an alpha source aiming alpha particles at a gold foil. Behind it, there was a detector that could measure the amount of alpha particles at various different angles. What were some of the observations and conclusions? So importantly, most of the alpha particles passed straight through, indicating that the nucleus is mostly empty space. Very few of the alpha particles were deflected by a large angle, meaning that the nucleus must have a positive charge which was repelling the alpha particles, since positive and positive repel. And since most of the alpha particles passed straight through, that means that also most of the mass must also be concentrated in that small nucleus. Our knowledge and understanding of the structure of the nucleus has changed over time. The previous model was actually known as the Plum pudding model. In that model, atoms were tiny spheres, with the dough being the positive charge and electrons being like the plums. This was actually motivated by the discovery that electrons can be removed from an atom, and it was an attempt to explain it. However, if the Plum pudding model was correct, Rutherford should have seen all the alpha particles just pass straight through, but that was not the case. Some of the particles were deflected at very large angles. Even a very small proportion of them actually deflected back with an angle of deflection of 180 degrees, which would have indicated a direct hit with the actual nucleus. And now let's have a look at the properties of alpha, beta, and gamma radiation. Those are the individual symbols, as you will be familiar with them from your GCSEs. Remember, alpha radiation is 2 protons and 2 neutrons, which is also a helium nucleus. It has a relative charge of +2, and it has a relative mass of 4 unified atomic mass units, i.e. a total mass of roughly twice the mass of a proton plus roughly twice the mass of a proton. A beta minus particle is simply an electron. It has a relative charge of -1, and very often its mass is negligible in some of our calculations. A beta plus is a positron, which has a charge of +1 and also exactly the same negligible mass because it's the antiparticle of the electron. Finally, we have gamma radiation, which is just high energy electromagnetic photons. It has a charge and a mass of 0. Notice how in this table we have used the unified atomic mass unit. It is defined as 1/12 of the mass of the unbound carbon-12 nucleus. In practice in questions, we take it to be approximately the mass of 1 nucleon. 1 U is 1.661 times 10 to the minus 27 kilograms, and that is given in your formula booklet. For instance, the mass of the alpha particle is approximately 4 times this number. Some simple absorption experiments can determine what type of radiation we are actually dealing with. So for instance, alpha particles are absorbed by a few centimeters of air or by paper. Beta minus particles are going to be absorbed by approximately 3 millimeters of aluminium foil paper or steel. If you're wondering about beta plus, should we just add that in? Beta plus particles will typically annihilate since they are antimatter. Gamma radiation is the hardest to be absorbed. It requires lots of centimeters of lead or meters of concrete. In terms of their ionizing power, the most ionizing is alpha radiation, followed by beta minus, and then finally we have the least ionizing, which is gamma. Let's do a practice question. A background radiation count is measured at 10 counts per second. When no material is placed between the Geiger counter and the radioactive source, the count rate is 500 counts per second. Okay, so adjusted, this will be around 490 or so. When 3 millimeters of aluminium foil is placed in front of the detector, the count rate drops to 250 counts per second. This statement here is telling me that beta radiation is present, because the beta radiation would have been absorbed by the foil. When the foil is removed and then a 1 centimeter of lead is placed, the count rate drops to 50 counts per second. So some of the radiation goes even through a centimeter of lead. This tells me that this can only be gamma radiation. So we definitely have beta and gamma. When the lead is removed and just a thin sheet of paper is placed between the counter and the source, the count rate is 200. So even the thin sheet of paper has stopped some of the radiation, meaning that alpha radiation must also be present. What types of radiation are present? Well, the answer is alpha, beta, and gamma. And now we're going to cover the inverse square law for gamma radiation. On the left-hand side of the equation, we have intensity. This is simply the power per meter squared, and hence it is measured in watts per meter squared. K will be a constant of proportionality, which will have units of watts, and in reality will simply be the power of the source. And finally, X is the distance to the source measured just in meters. Just a little note about graphical analysis. Typically, you will see graphs of intensity against 1 over x squared. So if this here is on the y-axis, if 1 over x squared is on the x-axis, that means that our gradient will just be k. And if this relationship is correct, the graph will be a straight line through the origin. Let's do an example question. A gamma source emits uniformly in all directions. The source emits 8,000 gamma photons in 2 seconds. Before we even move on, I'm just going to write down that that means that it emits 4,000 gamma photons per second. We need to calculate how many photons pass through an area of 0.35 square meters at a distance of 1 meter away from the source every minute. Let's just first visualize the problem. Here is our source. Let's put a little area across here, which is going to be 0.35 square meters, with this distance here being 1 meter. This area will just be a proportion of the entire radiation, which will be uniformly distributed around the sphere of radius 1 meter. The surface area of that sphere will simply be 4 pi r squared. So the amount of photons that pass through this area will simply be related to the proportion of the areas. We're going to have 0.35 divided by 4 pi 1 squared, which is just 4 pi. This here will be a fraction of the total amount per second, which is 4,000 photons per second. And to get the amount of photons per minute, we just need to multiply this by 60, giving us around 6,684.5, well, shall we just call that 6,700 photons. We also need to discuss safe handling of radioactive sources and some procedures for it. Usually the marks go for several factors. One is to maximize the distance between you and the source. For instance, we could use tweezers to handle the source, and we can keep at least 2 meters away when observing. We also need to limit the exposure time during the experiments. For instance, we can remove the source from the lab when it's not in use. We would never point the source at a person, and it's a good idea to stand behind a LED absorber. Another piece of good practice is to post a warning notice on the door that radioactive sources are in use. And let's talk about background radiation. What are the sources of it? Number one is probably the ground. Most rocks do contain radioactive materials. We also have cosmic radiation, which are highly energetic particles coming from space. The radiation is actually produced when they collide with elements in the atmosphere. We can also have carbon-14 from things such as living plants and animals. That also does technically arrive from the atmosphere, but it's another source of it. So how do we remove the background radiation from calculations? Well, in order to do so, we'll need the background radiation count rate. We need to take 3 readings of the count rate with a Geiger counter but with no source. And then we would find the mean. Afterwards, we'll subtract this mean from each subsequent measurement that we make. If we're asked on how to eliminate systematic error from the background count rate measurements, we need to ensure that we've removed all radioactive sources from the room. We ensure that the counter and the stopwatch are reset before measurement to avoid 0 errors. To reduce the percentage uncertainty in the count rate measurements, we want to use a longer integration time. For instance, if we're measuring for 10 seconds our count rate, we could do so for much longer time, such as 100 seconds. And let's talk about the balance between risk and benefits in the uses of radiation in medicine. Radioactive sources suitable for use in medical diagnosis must have the following qualities. They must be pure gamma ray emitters. This is because gamma rays are weakly ionizing. That means they would cause less damage. They can also escape the body and be detected. Typically, a pure gamma source would be injected into the patient in small doses. This would allow the imaging to take place via something known as the gamma camera. Because of that, they should also have low toxicity. The half-life must be short enough not to remain in the body for very long after the diagnosis, but it must be long enough for the diagnosis to be able to take place. And now let's start talking about radioactive decay. Radioactive decay is random. You cannot predict when an individual nucleus will decay. It is also spontaneous, meaning that it cannot be influenced by external factors such as temperature, pressure, etc. The word radioactivity comes from, well, activity, which is the number of particles emitted per unit time, and that number is always decreasing. The equation for it is simply that activity A is minus the rate of change of the particles. This here is essentially the number of particles emitted. This here is the time that's elapsed. The negative sign indicates that it is decreasing with time. The unit of A, the activity, is simply known as the becquerel. If we think about it though, the number of particles is unitless, so 1 becquerel is equivalent in SI base units as seconds to a power of -1. Another equation which is really important for activity is that activity is equal to lambda multiplied by n, where lambda is known as the decay constant. The definition of the decay constant is that it's the probability that an individual nucleus will decay per unit time. N in this equation is the number of particles left. The units of lambda include seconds to a power of -1 because it's just probability per unit time. It's also often given in hours to a power of -1 or potentially years to the -1 as well. We can combine those two equations. Let's see where I should write this. I'm going to write this over here to say that delta n over delta t, we'll just bring in the negative sign onto the other side, will be minus the decay constant multiplied by n. And this equation here is given in our formula booklet. We can also do a little summary of some of the radioactive decay equations. Another radioactive decay equation is how does the number of particles change with time? Well, the decay is actually exponential. We're going to get an exponential curve. That exponential curve means that we're going to be using the exponential equation. N is equal to n naught e to the minus lambda t. And here really is a function of time. So this here is the number of particles at time t. N naught is the number of particles at t is equal to 0, or often we can just write the initial number of particles. Lambda, as we said, is simply the decay constant, and t here is the time. Since A is lambda n, we can also write exactly the same equation. It also holds for the activity. A is equal to A naught e to the minus lambda multiplied by t. Very often we may have to use this equation and rearrange it for t. So let's do that. My first step would be just to isolate the exponent. So I'm going to go n over n naught is equal to e to the minus lambda multiplied by t. Then I will take the natural log of both sides. Ln of n over n naught is equal to ln e to the minus lambda t. Remember, ln and e are inverse functions. So essentially we can do this. We can go ln of n over n naught is equal to minus lambda t. The negative sign actually flips the exponential, giving us ln of n naught over n is equal to lambda multiplied by t. Finally, we can say that the time t will be given by ln of n naught over n divided by the decay constant lambda. Next, we're going to be discussing half-life. Half-life is defined as the average time taken for the number of nuclei to halve. Very often, it is simply given the symbol T-half, where this here is just a subscript. In the formula booklet, you're given the equation that T-half is equal to Ln of 2 over the decay constant. Let's show that this equation is true. We're going to start off by using our decay equation that n is equal to n naught e to the minus lambda multiplied by t. Then we can say that n over n naught is equal to e to the minus lambda t. But when the time is equal to the half-life, n over n naught as a fraction should be a half. So 1 over 2 is equal to e to the minus lambda. Now we're going to take the ln of both sides. We're going to get ln of a half is equal to the ln and the e will undo the effect of one another. Minus lambda t half. The negative sign will flip the ln. So we get ln of 2 is equal to lambda t half. Then our final step, let's just do this here. T half will be equal to ln of 2 divided by lambda, which is the equation that we're given. Let's do a simple but very important question. Every time we have the half-life of a substance, we also have the decay constant. For instance, carbon-14 has a half-life of 5730 years, and in order to calculate the decay constant, we can just use the fact that T half-life is equal to ln of 2 divided by lambda. The decay constant lambda is just then equal to ln of 2 divided by T half-life, and because the unit here is given as years to the -1, I'm going to leave that in years. If it was in seconds to the power of -1, I would change it, giving us approximately 1.21 times 10 to the -4 years to the -1. The next one is slightly trickier. We're once again given that carbon-14 has a half-life of 5,730 years, but this time we need to calculate the total activity of 1 kilogram of carbon-14. So for these questions, we need to use the equation that the total activity is equal to the decay constant multiplied by the number of particles. To work out the decay constant, we're going to use exactly the same method, which is going to be ln of 2 divided by T half-life. But this time the half-life will be in seconds because our answer needs to be in becquerels. To work out n, which remember it's the number of particles, we're going to divide 1 kilogram by the mass of carbon-14. Since we're not given the molar mass, our best approximation would be to use 14 times the unified atomic mass unit. And our total mass is simply 1 kilogram. Let's put both of these together into one equation. So because A is equal to lambda multiplied by n, we're going to get natural log of 2 divided by 5730, that's years. So multiply this by 365, 24 hours each. 3,600 to convert that to seconds, and then multiply this by 1.0 over 14 times 1.661 times 10 to the -27, and we should get an answer of right around 1.6 multiplied by 10 to the power of 14 becquerels. Another similar example. Technetium-99m has a half-life of 6 hours and a molar mass of 99 grams per mole. We want to calculate the total activity of 5 grams of technetium-99m in becquerels. Once again, we're going to use the fact that activity is equal to the decay constant multiplied by the number of particles. To work out the decay constant, we just do ln of 2 divided by the half-life, which is just 6 hours multiplied by 60 times 60 to convert that to seconds. To work out the number of particles, we need to use total mass divided by the molar mass multiplied by Avogadro's number. Because we're working in grams, I can just go 5 grams over 99. This is going to give us the fraction of the number of moles. Multiply this by Avogadro's constant, which is 6.02 times by 10 to the power of 23. And this here will give us a total activity of right about 9.8 times 10 to the power of 17 becquerel. We can very easily work out the half-life from a decay exponential curve. For instance, in this case, we've started with 100 particles, and at a certain time, we are going to have half of that, which is 50. So all we need to do is go across and then determine the amount of half-life from the axis of that graph. In other cases, we're also given a logarithmic graph such as this one. We have the natural log of n against t. Please note that this could also have been the natural log of a against t, and the mathematics will be exactly the same. How can we figure out the half-life from this graph? Well, remember that n is equal to n naught e to the minus lambda t. Once again, we're going to just isolate the exponential. So we're going to do n over n naught is equal to e to the minus lambda t. Take the natural log of both sides. The natural log and e essentially cancel out, leaving us just minus lambda t. But now I'm just going to use the property that Ln of something over something is equal to Ln of n, take away Ln of n naught, and this here is equal to minus lambda t. Now let's rearrange for whatever is on the y-axis, which is Ln of n. So I'm going to make Ln of n the subject of this equation, giving us minus lambda t plus Ln of n naught. And look at this. If we write underneath y is equal to mx plus c, Ln is on the y-axis, t is on the x-axis. This means that our gradient is equal to the negative decay constant. This makes sense because we can see that our gradient will be negative. Our intercept c is actually Ln of the initial number of particles, which also makes sense because the graph starts over here. Once we have the decay constant, which is the negative gradient, we can just use the fact that t half-life is equal to Ln of 2 divided by the decay constant, which is equal to Ln of 2 divided by the negative gradient, and this here is going to give us the half-life. Once again, we've covered another graphical method of determining the half-life. We also need to talk about radioactive waste. The source of radioactive waste are typically fission fragments from the fission of uranium-235 in fuel rods, but it could also be other sources. In terms of treatment, the waste is first cooled with water in a cooling pond, which is quite close to the reactor, and this happens for a number of years. The high-level waste is then usually made solid into glass, and then it's placed into concrete containers. There's lots of problems dealing with this waste. Because it's initially very radioactive, it needs to be remotely handled to avoid any human contact. And of course, the waste will be radioactive for a very long time, hundreds, maybe thousands of years. Transporting the waste is potentially a danger to the public as well, and it's something that needs to be taken care of. We're going to use this notation to figure out what's inside of the nucleus. Over here we have the proton number, and up here we have the nucleon number, which is essentially the number of protons plus neutrons. For instance, this nucleus has 92 protons, therefore it will have a charge of plus 92e, where E is just the elementary charge, and it will also have 238 take away 92, which is 146 neutrons. Uranium will decay via alpha decay. This means that it will release an alpha particle, which, remember, is just the nucleus of a helium atom, so it'll be a 4 and a 2, meaning that it has 2 protons and 2 neutrons, overall 4 nucleons. What's left is actually thorium, and thorium will have 238 take away 4, which is 234 nucleons, and 92 take away 2, which is just 90 protons. Another possible way to decay is via beta minus or via beta plus decay. Remember, the fundamentals are as follows. In beta minus, would have a neutron turn to a proton. The neutron is a 1 and a 0. The proton is a 1 and a 1. So we're going to need something negative. Well, this here will just be the electron minus 1, 0. And we need to conserve lepton number. So we're going to need the antiparticle, which is the anti-electron neutrino. The reverse is also possible. A proton can turn into a neutron. The proton is a 1 and a 1. The neutron is a 1 and a 0. So we'll need a positron like so. And then to conserve lepton number, we're going to need a neutrino. And remember, the electron is simply known as a beta minus particle. And this here hence is known as beta minus decay. And the positron is also known as a beta plus particle and hence beta plus decay. Here's an example question. We need to determine X and Y, and we have the following reaction. Carbon-14 has decayed into nitrogen, and then it has also released a beta minus particle and an antineutrino. Well, this is beta minus decay, so this here is telling me that a neutron has turned into a proton. The total nucleon number in both types of beta decay remains exactly the same, so X is just going to be 14. Y, on the other hand, will increase by 1, so that's just going to be 7 because one neutron has turned into a proton. Another process that we need to know is electron capture. It's the process in which a proton-rich nucleus will absorb one of its own inner atomic electrons. The proton will turn into a neutron. Typically, you also have gamma radiation being produced. It could also be X-rays. In this process, one of the protons will actually turn into a neutron. So this here will change to cobalt. And since one of the protons has turned into a neutron, this number here will be 27, the proton number. The nucleon number will remain unchanged. We also need to conserve lepton number, so that's why we're also going to get a neutrino. And also some excess energy, typically as gamma ray photons or X-ray photons. Should we just write down that it has decreased because the proton has turned into a neutron? And let's look at the graph of the number of neutrons against the number of protons. If we were to plot these for all the elements, we would actually get a curve which deviates from the straight number of neutrons is equal to number of protons line. This is because as the proton number increases, we need more strong nuclear force to keep the nucleus stable, and the neutrons are providing that. And this line over here, this yellow line, is the line of stability. If we are above this line, we have an excess number of neutrons, more neutrons than protons. Therefore, that means that beta decay will be far more likely because a neutron will be turning into a proton. On the other hand, if we're below this line in this region somewhere over here, then there will be an excess of protons, so beta plus decay will be far more likely, i.e. a proton turning into a neutron. Some of the very heavy nuclei will decay via alpha decay. They are becoming very large, and it's far more likely for them to escape the strong nuclear force by ejecting an alpha particle. Sometimes we get describe and explain questions on the forces within the nucleus and quoting their range. First of all, we have the electromagnetic force, which is repulsive, and it acts between protons. It also has an infinite range. The more protons we have, the higher the electromagnetic force of repulsion. So it increases with the proton number. Counteracting this, we have this strong nuclear force which acts both on protons and neutrons. It is attractive up to 3 femtometers, 0 beyond, and is repulsive below 0.8 femtometers. The final repulsive portion just ensures that there is not a total collapse of the nucleus. In general, more neutrons are needed to hold the nucleus together and contribute to the binding strong nuclear force. Fewer protons are required in order to reduce the repulsion. And this is what keeps the nucleus in balance. And now we're going to have a look at nuclear energy diagrams. These look intimidating at first, but they're really similar to the atomic electron energy level diagrams. In this particular case, we are given the actual energy differences. However, we may also be given a scale on the left-hand side, and if that's the case, all we need to do is take away the numbers from this value and that value to work out the energy differences between them, or any other value as well, of course. Over on the left, we'll typically have a material that's about to decay, and in this case, it can release a beta minus particle to either one of those two excited energy levels of nickel 60. If it decays to the first one, it's going to release a beta minus particle with an energy of 0.31 mega electron volts. And then typically 2 separate gamma photons will be released as the nucleus first decays to the next energy level and then finally towards the ground state. It's also possible that cobalt-60 will decay to the other excited energy level, releasing a beta minus particle. And what we need to do for the first part of this question is, using the diagram, state the maximum energy of an emitted beta minus particle during the decay. Well, the maximum energy will occur when the beta minus particle decays to this decay because there's a larger energy gap. And that energy gap will be equal to the sum of the previous two. So it will just be 1.17 plus 0.31, which is just going to give me 1.48 mega electron volts. For the second part, we need to calculate the maximum frequency of a gamma ray photon during this decay. Well, the maximum frequency really corresponds to the maximum energy gap, but during this decay, there will only be one gamma ray photon emitted with an energy of 1.33 mega electron volts. But if a 1.33 mega electron volt photon is emitted, we can just simply use E is equal to HF to determine our answer. The frequency will just be equal to E over H, and there will typically be a little trick with the units. We may have to convert from mega electron volts, or maybe there might be a power up here, something to be aware of. Okay, so the energy will just be 1.33 mega is times 10 to the power of 6. Elementary charge is 1.6 times 10 to the power of minus 19. Divided by Planck's constant, 6.63 times 10 to the power of minus 34. And this here will give us a frequency of 3.2 multiplied by 10 to the power of 20 Hertz. Please note that if we're just being asked to find the wavelength, we'll just use the equation E is equal to Hc over lambda instead. We also need to know that nuclear excited states are used in medicine. For instance, technetium-99m emits pure gamma rays via these excited states, which are used in medical imaging. They can pass straight through the body and then they can be detected by a gamma camera. The half-life of technetium-99m is also long enough for imaging to be able to take place, but not too long so as to cause damage. And now let's talk about estimating the nuclear radius. This can be done in a number of different ways, and one which is often tested in exams is the estimation using the closest approach of alpha particles. Imagine that we have some gold nuclei across here. The proton number, by the way, of gold is 79, so they will have a charge of 79e or plus 79. And then we also have an alpha particle, which is a 4 and a 2, so it will have a charge of plus 2. And let's say that it's initially moving with a kinetic energy of 7.7 mega electron volts. Electrostatic repulsion will be slowing down the alpha particle as it's moving this way. Eventually it will reach a spot, let's say over here, and we can use that distance of closest approach to estimate the size of the nucleus. In reality, these distances are very tiny, and this diagram is not to scale. The way we do this is we set the initial kinetic energy to the electrostatic potential energy. Sometimes when we be given the speed of the alpha particle, we'll have to calculate it separately using a half mv squared. But in this case, this is simply just 7.7 mega electron volts. Now the equation for potential energy that we're going to use, well, this is just equal to Q multiplied by delta V. And we'll just take the potential to be Q over 4 pi epsilon naught R. So the electrostatic potential energy is just Q over 4 pi epsilon naught R. This equation is not given in the formula booklet, but you do need to know this for the exam. So we know that our kinetic energy is going to be equal to QQ over 4 pi epsilon naught R. And we're just looking for the distance of closest approach, which is R. So let's just rearrange for R, which will be QQ over 4 pi epsilon naught multiplied by the kinetic energy. Now, one of the Q's will be 79. If the substance is different other than gold, it will be a different number, but this number will be given in the question, multiplied by E, where E is the elementary charge, and then the other one will be the charge of the alpha particle, which is just 2e. We're going to divide this by 4 pi epsilon naught times the kinetic energy, which is 7.7, mega is 10 to the 6, multiplied by the elementary charge, E. Shall we just cancel one of those E's across here? Okay, this one here will just give me 79 times 2 times 1.6 times 10 to the negative 19. Divide that by 4 pi, 8.85, 10 to the negative 12. Multiply this by 7.7 times by 10 to the power of 6. And if we do this up to a couple of significant figures, we're going to get around 3.0 times 10 to the power of minus 14 meters. For the exam, we also need to know typical values for the nuclear radius. These are about 10 to the power of minus 15 meters or a femtometer. Please know that for larger nuclei, something like uranium, you might be expecting something more like 10 to the power of minus 14 meters. There is an equation for the nuclear radius in terms of the nucleon number. Over here on the left, we actually have the nuclear radius. R0 is just a constant that has units of distance and is typically about a femtometer. We very often have to work it out using the question, so please don't just memorize that value. A is the nucleon number. And it's really important that this formula here is empirical, meaning that it is derived from experiments. Let's do an example problem. The radius of carbon-12 is 2.86 times 10 to the power of minus 15 meters. And what we need to do is to calculate the radius of carbon-14. There's a few different ways of doing that. First, I'd quite like to determine the value of R0. I will just do R is equal to R0 A to the power of a third, meaning that R0 will just be the radius over A to the power of a third, i.e. 2.86 times 10 to the minus 15. Divide that by A, which is going to be 12 raised to the power of a third, giving us around 1.25 times 10 to the power of minus 15. Now that we have the value of R0, we can just plug it into the equation for the radius of carbon-14 yet again. So we can just say that R, the radius of carbon-14, will just be equal to R0, which is 1.25 times 10 to the power of minus 15. Multiply this by A, which for carbon-14 is now going to be 14 raised to the power of a third. And this here will give us 3.01 times 10 to the power of minus 15 meters. Please note that this constant here, R0, is a really good estimate for the radius of hydrogen-1. When the nucleon number A is simply equal to 1, then R is equal to R0, which is about this value here, which is the radius of hydrogen. The next derivation typically comes as a show question. We're going to use the equation of nuclear radius to show that nuclear density is independent of the nucleon number. So we're going to state that density is equal to mass over volume. We're going to assume that the nucleus is a sphere, therefore the volume of a sphere is just 4/3 pi multiplied by r cubed. Remember though, now we've got an actual formula for the radius. R is equal to R0 A to the power of a third. And we'll be able to sub this formula into here. What about the mass though? Well, a really good estimate for the mass will be the nucleon number A multiplied by the unified atomic mass unit, which is U. You can think of it as the mass of an individual nucleon, and if we multiply this by A, we are going to get the mass of the entire nucleus. So if we plug both of these into our original equation for density, we're going to get AU over 4/3 pi. And then rather than R, I'm going to put some brackets. I'm going to say R0 A to the power of a third cubed. Okay, well, we can see that this will be equal to AU over 4/3 pi R0 cubed A raised to the power of a third cubed just gives us A. And notice how A cancels, therefore the density is independent of the nucleon number A. We have made a very important assumption in this derivation though. We have actually assumed that the mass of the proton is approximately equal to the mass of a neutron, which is approximately equal to U. This is only approximately correct, and this assumption typically needs to be stated in our show question, as there is a small difference between those two relative masses. We also need to remember the shape of this graph of electron diffraction by the nucleus. On the y-axis, we have the relative intensity, and on the x-axis, we have the angle of diffraction. A couple of key features include that the central maximum is approximately twice as wide. Occasionally, we can get also questions on estimating the radius of a nucleus using this graph. Questions may give us the angle from the central position. Let's just call this angle theta or delta theta. Once we have this angle, we can actually use the equation that sine of theta is approximately equal to 1.22 multiplied by the wavelength divided by 2r. In this case here, lambda is just the de Broglie wavelength of the electron. R here is the radius of the nucleus. And theta, well, theta is just this angle here from the central max to the first minimum. If we have to take it from a graph, it will be across here. We can use the standard formulae from quantum physics and from our formula booklet to determine the de Broglie wavelength. Next, we're going to be looking into mass and energy, including the famous Einstein's equation that E is equal to mc squared, how mass and energy can be converted from one to another. In fact, a binded nucleus will have a lower mass because some of that mass has been converted to energy, which brings us to this classic state question: what is meant by binding energy? It is the energy or work done required to separate the nucleus into its individual protons and neutrons. In this part of the spec, we're going to be using the unified atomic mass unit quite often. One unified atomic mass unit is 1/12 of the mass of the unbound neutral carbon-12 nucleus. In practice, we often use it as the mass of one nucleon, which will be either an individual proton or a neutron. In the formula booklet, we're also given the value of one unified atomic mass unit, which is approximately 1.661 times 10 to the minus 27 kilograms. There is another really important conversion in your formula booklet. I'm going to write this in a different color. Since E is equal to mc squared, we can actually see the associated energy with one atomic mass unit. And the conversion factor is really useful in calculations. Then the energy associated with this will be 931.5 mega electron volts. If you're wondering where this number comes from, I will leave the calculation over here. Please note that if you put this into a calculator, I think you're going to get around 934, but this is because our constants here are not as accurate as they can be. If we were to plug in constants to higher degree of precision, we're going to get 931.5, but as we said, this number is given in the formula booklet. And we'll now have a look at mass difference. This is simply the difference in mass between the nucleus and then the mass of the individual nucleons. I often take the mass of the individual nucleons and then take away the mass of the nucleus, as it will just give me a positive number. Let's calculate the difference using the following table. We have a alpha particle and we're given the mass in unified atomic mass units. And then we have some protons and some neutrons. The mass difference will simply be the mass of the individual nucleon, so that will be 2 times the mass of a proton plus 2 times the mass of a neutron. Take away the mass of an alpha particle. Let's plug in some of those values. We are going to get 0.03039 U. And here's a really important trick which is going to save you a ton of time in exams. If we have the mass difference in unified atomic mass units, we can calculate the binding energy directly, because we know that 1 U corresponds to 931 0.5 mega electron volts. So therefore, all we need to do is take our mass difference 0.03039 and then multiply this by 931.5, and this here will give us around 28.308 mega electron volts for the binding energy in mega electron volts. We can also calculate binding energy without this conversion factor. And even if it's easier with it, let me show you how to do it without. So we want to calculate the binding energy for the nucleus of iron 56, and we're given that the mass of the iron nucleus is 9.27 times by 10 to the power of minus 26 kilograms. Our first step would be to calculate the mass difference. Okay, well, this here will just be 26 times the mass of a proton. We know this because it's element 26. And there will also be 30 neutrons because 56 minus 26 is just 30. So let's just add up 30 times the mass of a neutron. Then let's take away the mass of the iron nucleus, which let's just call it MFE. Okay, let's plug in some numbers using the formula booklet. Okay, plugging in those values, we are going to get around 1.048 times 10 to the power of minus 27 kilograms for our mass deficit. I'm going to keep this to a relatively high number of significant figures for now because we're not quite over with the calculation yet. Our step 2 will be to simply use E is equal to mc squared. Our m is just going to be our mass deficit, so that's going to be 1.048 times by 10 to the power of minus 27. Multiply that by c squared times 10 to the power of 8, all of it squared. And then because we want our final answer in mega electron volts, I am just going to divide this by 10 to the power of 6, which is because of the mega, and then the electron volt, that's 1.6 times 10 to the power of minus 19. And up to two significant figures, we're going to get an answer of around 590 mega electron volts. The two major reactions that we'll be looking at are nuclear fusion and nuclear fission. Nuclear fusion occurs when two lighter nuclei combine to produce a heavier nucleus, whereas nuclear fission occurs when a heavy nucleus will split into lighter nuclei. And here's a really common question. Explain why energy is released in the fusion of two nuclei. The way to answer this is that the total mass of the nuclei is more than the mass of the product. And the binding energy per nucleon increases when a nucleus is formed in fusion. In order for energy to be released, the binding energy per nucleon needs to always increase, and this is also true for fission. If energy is released by fission, then the binding energy per nucleon will also increase. And this is clearly shown in this very important graph, which showcases the average binding energy per nucleon against nucleon number. Notice how the peak of the graph is at iron 56, which is the most stable element, the one with the highest average binding energy per nucleon. Elements to the right cannot yield energy through fusion because the binding energy per nucleon decreases. So therefore, this region over here is the fission region. Elements to the left cannot yield energy through fission as the binding energy per nucleon also decreases. In other words, this here is the fusion region. A good rule of thumb is if two elements undergo fusion, the binding energy per nucleon needs to be high in order for energy to be released. Or through fission, if we had an element over here that splits up into two lighter elements, we can see that the binding energy per nucleon increases. Notice how this gradient, this relative gradient of the tangent at each point, fusion releases more energy as the binding energy mass difference for lighter nuclei is much greater. It does require extreme conditions though. You need to overcome the electrostatic repulsion, therefore you need very high temperatures and very high pressure, the exact conditions you will find in the core of a star. We can also calculate the energy released in fusion and fission reactions. Here's an example fission reaction of uranium-235. And we're also given a list of masses over here. Our first step in working out the energy released would be to calculate the mass difference. In this case, we're given all these values in unified atomic mass units, but we could also do this in kilograms and use E is equal to mc squared. Let's work with those units though. So we'll need the mass of a neutron plus the mass of uranium. And then from that, we're going to take away the mass of Ba barium plus the mass of Kr, and then plus the mass of 3 neutrons, close the brackets. Essentially the total mass on the left, take away the total mass on the right. Let's change that to 3 times the mass of a neutron to be more specific. Now we're ready to plug in lots of numbers and be really careful with our calculations. And we're going to get approximately 0.1866 U. But remember, 1 U corresponds to 931.5 mega electron volts. So to work out the energy in mega electron volts, all we need to do is multiply 0.1866 times by 931.5, and we're going to get approximately 173.818 mega electron volts. The reactions inside a fission reactor are known as induced fission chain reactions. It starts off with a single thermal neutron that is absorbed, and that creates a heavier, unstable nucleus which tends to undergo fission. It splits into 2 lighter nuclei, the energy is released together with more neutrons. The process then repeats itself and more energy is released, and it's important to control it. We also need to know some specifics on the components of a nuclear reactor. First of all, we have the moderator. The actual fuel rods containing uranium nuclear field are placed within the moderator. It's very often water, so it slows down the neutrons via elastic collisions. And the most efficient way to slow them down for the neutrons would be to collide with particles of similar mass. This is really important, and this is why we have chosen typically water, because the mass difference is not that drastic and the moderator slows down the neutrons very efficiently. Because of this, it can also not be heavier or lighter than much lighter, should really add much over here, compared to the mass of a neutron. In terms of the control rods, well, we're going to need to control the reaction. In order for the rate of reaction to be stable, you need a minimum amount of fuel, and this is known as the critical mass. At the critical mass, there's a steady rate of essentially production of energy. The reactors tend to have more than this amount, but then you can control the rate of reaction by lowering down control rods which absorb the neutrons. They're typically made out of boron, which is a material which absorbs neutrons, and hence you can actually control the reaction rate. You also have the coolant. It's around the reactor core, and that removes heat produced by the fission process, typically a liquid or a gas. Very often it could even be steam from the actual moderator. Its job is to simply remove heat energy away from the reactor. There are lots of benefits in using nuclear power. For instance, there's less greenhouse emissions compared to many other forms of electricity generation. There's also a much smaller amount of fuel required to produce vast amounts of energy, and this is because, well, E is equal to mc squared. So we get that factor of c squared. It can also be produced continuously without having to rely on wind and power. And as an extra benefit as well, we can also get the production of medical isotopes, which can then be used in nuclear medicine. Okay, folks, so very well done for revising an entire topic. If you're revising for paper 2 or 3, well, you will find my video on the whole of magnetic fields really useful, and I'm leaving this somewhere over here. Good luck in your revision.